Lesson 1: Atmospheric Structure. If you are able to describe, define, state, and differentiate the learning objectives, you have complete mastery of the material. We will not be covering all of the layers of the atmosphere in this lesson, only the stratosphere and troposphere. The Earth is covered in gaseous layers. The portrayed layers are on the left-hand side of the graphic. On the right-hand side is the actual thickness relative to the size of the Earth, but it's easier to see them when we expand them in the portrayed atmosphere. The first layer that's adjacent to the surface of the Earth is the troposphere. There's a lot of moisture and condensation in the troposphere, which is where all weather occurs. You can see from the diagram the anvil top, or the upper portion of this cloud, reaches into the stratosphere, and that is the exception to the rule. Otherwise, the weather occurs in the troposphere. Its height on average is 28,000 feet over the poles, 55,000 feet over the equator. Temperature normally decreases with altitude, which we call a lapse rate, or the change in temperature with increasing altitude. Winds will increase with altitude. So as you go up, temperature decreases and wind speed increases. The tropopause, labeled at this point on the graph, is where that change in lapse rate occurs, from the standard lapse rate to an isothermal lapse rate. The isothermal lapse rate begins with the tropopause at an average height of 36,000 feet MSL over the US. You will frequently find turbulence, contrails, and haze at the tropopause. Jet stream winds occur just below the tropopause and within the troposphere. The stratosphere is the next layer above the troposphere, separated by the tropopause from the troposphere. It's characterized by smooth flying conditions and excellent visibility. It begins as isothermal at approximately 36,000 feet over the US, and at approximately 66,000 feet, it stops being isothermal and begins to become a temperature inversion, meaning that temperature increases as you continue to increase in altitude. There's few aircraft that can actually fly in the stratosphere. Most of our flying takes place within the troposphere, but if you find yourself up in the stratosphere, it will be smoother and better visibility. The average top height of this layer over the US is 158,000 feet MSL. Overall, the stratosphere is characterized by an inversion, but it's important to note that it first starts off as isothermal and then becomes an inversion. The inversion is due to the presence of ozone interacting with solar radiation. The composition of the atmosphere is a mixture of gases, 78% nitrogen, 21% oxygen, and a 1% mixture of 10 other gases. Water vapor comprises 0 to 5% of the atmosphere by volume. This graph depicts, once again, the standard lapse rate that occurs in the troposphere. On a normal day, with every 1,000 foot increase in altitude, the temperature will drop 2 degrees Celsius. So you see the graph starts at sea level at 12 degrees. By the time you get to 1,000 feet mean sea level, the temperature has dropped 2 degrees to become 10 degrees, and so on and so forth. You can also characterize this as an inverse relationship. Isothermal is shown on the graph as a vertical line, which depicts the relationship of temperature remaining the same with increase in altitude, However, you should note that it is not typical for it to be isothermal within the troposphere, only in the stratosphere immediately after passing into the stratosphere. And then once you reach the average height of 66,000 feet is where we see our temperature inversion. And the temperature will increase with altitude. We do not discuss a standard lapse rate for this inversion to take place, only that it occurs in the stratosphere and around 66,000 feet up to the top of the stratosphere. In which atmospheric layer does weather normally occur? The troposphere. The stratosphere is characterized by smooth flying conditions and excellent visibility. Next, we'll talk about atmospheric pressure. This is the pressure exerted on the surface by the atmosphere due to the weight of a column of air directly above that surface. It always decreases with increasing altitude, meaning you will never be at an area of higher pressure than what is below you. Its units of measurement are inches of mercury, Hg for short, and millibars, or MB for short. We have some standards that go along with atmospheric measurement on what we consider to be a standard day or standard day conditions. A standard sea level pressure at mean sea level is 2,992 inches of mercury. We typically do not state the decimal and only report it as 2,992. The equivalent to that is 1013.2 millibars, and you will not need to know conversions for the homework or for the test, but conversions are available in the Flight Information Handbook, which is a reference to this course. In addition to a standard lapse rate for temperature, we have a standard pressure lapse rate, and that is 1 inch of mercury, equivalent to 34 millibars, per 1,000 feet. The standard sea level temperature is 15 degrees Celsius, equivalent is 59 degrees Fahrenheit, and again, the standard temperature lapse rate is at 2 degrees Celsius per 1,000 feet increase in altitude, which is also approximately 3.5 degrees Fahrenheit. Station pressure is the atmospheric pressure at an airfield or station. So sea level pressure is equal to station pressure plus the equivalent difference in inches of mercury for that altitude. Sea level pressure is calculated by reading the pressure at mean sea level or by measuring it at the station and correcting it for the equivalent difference in altitude of the station. This is used for surface analysis charts. The way we calculate this is by using the equation sea level pressure is equal to station pressure plus field elevation. In this case, the station pressure at Denver would be 2,492 plus the field elevation converted to inches of mercury. 5,000 feet equals 5 inches of mercury. So we add 5 and we get an equivalent sea level pressure of 2,992. This is a surface analysis chart, otherwise known as a pressure chart or pressure distribution chart. And what it shows is areas of high and low pressure, lines of equal pressure known as isobars depicted in black, and then also ridges, troughs, and fronts with different symbology. The symbology is as shown. Blue H's depict areas of high pressure, red L's depict areas of low pressure. From these areas, we will see depictions of fronts, ridges, and troughs. It is important to note that there is a squall line depicted in this area as a purple dashed double dotted line. Purple is the incorrect color. They are actually depicted as red dashed double dotted lines for a squall line. That is a change. Here we have depicted the ridges and troughs. Ridges coming out of a high pressure center running perpendicular to the isobars surrounding the high pressure center. They look like a mountain ridge, which will help you to remember that they are associated with high pressure and good weather. A trough is a dashed line that comes out of a low pressure center, again running perpendicular to the isobars surrounding that low pressure center, and are generally associated with poor weather, and oftentimes you will see a front instead of the trough symbology. (15°C or 59 degrees Fahrenheit). Next, we'll talk about altitude measurement. The display is a representation of altimeter that you would see in the aircraft. The barometric altimeter displays altitude in feet instead of pressure, because to see it in pressure would not be useful to us. We fly typically at mean sea level altitudes on our altimeter. The setting should be nearly equal to station pressure corrected to mean sea level. In other words, it should be the equivalent pressure setting that you would see on the surface distribution chart. And that setting is input into this window here called the Kollsman window. Increasing the setting in the Kollsman window, done by spinning the knob in the lower left-hand corner of the barometric altimeter, will increase the numbers in the Kollsman window and also cause the needle to increase and show an increased altitude. Decreasing the knob will decrease the numbers in the Kollsman window, and the pointer will read out a lower altitude. It is calibrated for a standard lapse rate, so anything outside of that can induce a small amount of error. And it reads off in increments of thousands of feet in the large box, in hundreds of feet in the small box, which also corresponds to the numbers around the outside of the dial. Altitude is always given in reference to some base, and the reference which they refer to is what causes it to be called a certain type of altitude. Indicated altitude is the reference above what your altimeter is set at. So the indicated altitude is always read directly off of your altimeter in the cockpit, and it may be the same as your actual altitude above mean sea level, but in the case of non-standard lapse rates or wrong or erroneous settings in the Kollsman window, it could be different. True altitude, also given in mean sea level, is the actual distance you are from mean sea level. And the mean sea level is the same, although there may be terrain between you and mean sea level. To account for the terrain, we have absolute altitude, or AGL, which stands for above ground level. AGL altitude, or absolute altitude, is the distance directly beneath you, between you and the nearest point of land. Pressure altitude is the pressure above the standard datum plane. The standard datum plane is defined by where a equivalent pressure of 29902 would lie. At some point that may be below or above actual mean sea level. This reference is important for certain checks that take place in the aircraft, as well as testing the performance of the engines. Density altitude is not a direct reference to height, but a reference of aircraft performance. For example, at 5,000 feet MSL, if it is extremely hot and humid on that particular day, the aircraft may behave as though it is at 10,000 feet. That 10,000 feet is referred to as density altitude. So it is an indication of aircraft performance. When we fly from one area to another, we rarely see the pressure remain exactly the same. Therefore, we need to update our altimeter setting routinely throughout the flight, or as we travel from one location to another, or throughout the day as the pressure changes. Otherwise, we may continue to fly a set indicated altitude, but be flying at a different true altitude, meaning our actual distance above sea level and above the ground or terrain beneath us is different. We use the ditties high to low, look out below, or low to high, plenty of sky to describe how our true altitude changes when we change pressure. You will be doing these homework problems and on the test, and it's recommended to set it up in this way. You will be told where you're starting, where you're going to, what the field elevation is at your destination. You'll be given an indicated altitude that you're flying in between, what the pressure is where you start, and the pressure at your destination. So in this case, we'll look at the high to low, look out below. If you start off at a pressure of 3022 and you're going to an area where the pressure is 2992, you're going from high to low and you're going to look out below. You'll also be given a field elevation so that you can compute your AGL altitude when you arrive there. In this case, we will say 3,000 feet, and an indicated altitude or altitude assignment of 8,000 feet. So if you have the problem set up in this way, then you can answer these questions. First, what is the scenario? As we said before, the scenario is high to low. So you can draw your aircraft below your altitude assignment, indicating that you are now lower in true altitude than you plan to be. The second thing you have to find is what your altitude error is, and that is the difference between your starting and ending pressures. In this case, it's 0.3 inches of mercury. To account for the standard pressure lapse rate, we multiply times 1,000, and we get 300 feet of error. So we know that we are 300 feet lower than our indicated altitude of 8,000 feet. So to find our true altitude, in the case of a high to low scenario, we will take our indicated altitude, given in mean sea level of 8,000, and subtract our error of 300 feet to get 7,700 feet MSL, because it's still in mean sea level. That is our true altitude. Then we want to find out, if we continued to fly in this direction, what would our AGL altitude be when we arrived at our destination, our altitude above that field. And to get that, we take our true altitude of 7,700 feet and we subtract our field elevation of 3,000 feet to give us 4,700 feet. And again, this is an AGL because that is our distance above the field directly. And finally, the last question we may be asked or have to answer is what our altimeter would read if we were to land at our second station, and that will be again in MSL and be different from the field elevation because we did not update our altimeter setting. So if we still had 3022 in our altimeter and landed at our destination, the way we would figure out that answer is take our field elevation of 3,000 feet, and in this case we would add the error of 300 feet, giving us 3,300 feet MSL. So our altimeter would read 3,300 feet MSL on deck where the field elevation is actually 3,000 feet. But due to our incorrect altimeter setting of 3022, when the actual station pressure is 29902, our altimeter would. In this scenario, you can see
Navy Zero,
a
Fox
visual depiction of
511,
such
Mobile altimeter
showing the low
3020.
to high scenario. And as they play the video, you'll see the pressure increase. As the pressure increases, the altimeter will remain the same because the pilot will make adjustments to maintain their indicated altitude of 5,000 feet, which will result in the aircraft becoming high. Once they receive an updated altimeter setting of increased
Navy
value,
Zero, Fox
higher pressure,
511, Mobile
they will
altimeter
turn their knob
3020.
clockwise, increase the number in their Colesman window, which will cause the needle on their altimeter to rise, showing the pilot that they are high. Then they will adjust back down to their prescribed altitude of 5,000 feet. So let's see this as we play the video. Pressure increases, indicated altitude remains the same.
Navy Zero, Fox 511, Mobile altimeter 3020.
As they spin in the higher new altimeter setting, the needle climbs, indicating they are approximately 200 feet high, and then they descend back down. The same is true of differences in air temperature. As you fly from an area of higher temperature to lower temperature, your true altitude will actually become slightly lower than your indicated altitude. As you fly from an area of lower to higher temperature, your indicated altitude will remain the same and your true altitude will slightly increase. We do not typically account for these differences except in the case of extreme temperatures, which are considered below 0 degrees Celsius, and we can find reference and a chart for these temperatures in our flight information handbook pictured on the right hand side of the screen. With a pressure change of 1 inch of mercury, how many feet will the altimeter reading change? 1,000 feet. If the air is colder than the standard temperature, the aircraft will be blank than the altimeter indicates. And this indicates if you go from warmer to colder. And it is lower. High to low, look out below, applies to both air and pressure. This slide is a summary slide of the differences between traveling from high to low and low to high pressure for both calculating the amount of error, the actual true altitude, and the indicated altitude if you were to land at your destination field without adjusting the altimeter setting. In the case of going from high to low, you would look out below. So you would take your MSL assigned altitude and subtract the amount of error. The amount of altitude error is the difference in altimeter settings multiplied times 1,000 feet to account for the standard pressure lapse rate. Then, taking that true altitude, which you computed, you will subtract the field elevation of the destination you're going to. The difference between your true altitude and the field elevation at your destination would be your AGL, or absolute altitude, over your destination airfield when you arrive. And then if you completed your approach and landed safely on deck, again without updating your altimeter setting, when on deck, your altimeter will not read the correct field elevation because you have an incorrect sea level pressure setting. Therefore, you will take the sea level pressure correction. You will take the field elevation and add the error that you calculated to do your first step. And that would be the indicated altitude that would read on your altimeter on deck at the destination. Similarly, the opposite is true if you're going from low to high. You will find out what your altitude error is by taking the difference in altimeter settings and multiplying times 1,000. You'll add that to your assigned altitude in the case of going from an area of low to an area of high pressure. The AGL altitude will still be subtracting the field elevation from that true altitude, and the indicated altitude when on deck at the destination will be the opposite of the other scenario. You will take the field elevation and subtract your altitude error. In summary, we covered an introduction to weather and the atmosphere. We talked about the composition of the atmosphere, how we measure altitude and what references we use, and how we account for differences in pressure and temperature as we travel from one location to another. For our review questions, a condition where the air temperature aloft is higher than that of the lower atmosphere is generally referred to as a temperature inversion, meaning temperature increases with an increase in altitude. The standard temperature lapse rate of the atmosphere in degrees Celsius per 1,000 feet is 2 degrees Celsius, or approximately 3.5 degrees Fahrenheit. The height of an aircraft above the ground is known as above ground level, AGL, or absolute altitude. The decrease in atmospheric temperature with increasing altitude is called standard lapse rate. Any change in temperature with altitude is referred to as a lapse rate. The standard lapse rate refers to 2 degrees Celsius per 1,000 feet increase in altitude. Standard sea level pressure is 1013.2 millibars, or 2,902 inches of mercury.